So welcome, I think it's 3:30 now, so I'm going to start the talk. So the talk will be about what's new in version 10 about graph and networks. Oh, those lights I didn't notice the lights. Thanks. Okay. So as you all know, we introduced graph in version 8. So, graph objects start to be the first-class citizen in Mathematica and in the Wolfram language, if you put it that way, during version 8. And so essentially, the approach was to provide tools or functionality for modeling, analyzing, and synthesizing graphs, essentially, and networks in general. So we introduced about 150 functions. So that was a huge amount of work, a lot of new functionalities. And in version 9, we went one step further. So that was, version 8 was essentially put the framework in place. So in version 9, we tried to do a vertical, and the vertical we picked was social network. It was the hot topic at the time, and still, somehow. So we introduced a couple of functions about social network, analysis, centrality, and such. And we enhanced the modeling and analysis aspect in graph and networks. So, and in general, the frameworks, show that it's solid and it, we can build on top of it. So during version 10, we decided essentially to, instead of going vertically, kind of going back horizontally and try to enhance it more by introducing actually more functionality for modeling, more functionality for analyzing, and, specific domain application cases. So it's essentially that part I'm going to talk about, how we enhance the modeling and the analysis. But as, I want to point out from the start, you see that the number of functionality, the number of functions we introduced between those three versions actually dropped. But in behind the scene, the scope actually increased, and actually is what I will try to show you, that the system gets more smarter, and you get more, more power to actually, from the same set of functions, you can actually do more. So for version 10, we did a framework-wide support of multigraph and mixed graph. And I will show how we did actually that transparently and quite easily for you to just use, without actually modifying our workflow. And the next thing we actually did is we did a 3D graph visualization, which was a request from several users, since we already have 3D visualization in Mathematica, so that was one step close enough to get. But also that required a lot of work. I will kind of show the scope and what we did. And as usual, we introduced new capability. There's for sure several areas we haven't covered in earlier versions, so we decided to push and actually add more functionality in that direction. And as usual, we like to enhance the performance, make it faster and make it better for you and make it easier. So we improve the performance and usability of the functionality. And I hopefully kind of show some of those. And some people, if you actually use graph more often, you actually probably already notice that it gets more fluid, the way you actually use graphs. So let's start with one of the main functionality, which is the introduction of graph, and the fact that we build mixed graph and multigraph in the system. So what is a mixed graph, a multigraph? I will start there. So it's essentially a graph which has multiple edges. Oh. You will break my alignment, and I will blame you. Much better. OK. So essentially, we decided we have to introduce multigraph. So essentially, as you know, at least some people will not agree with me, but the world is not just based on sample graph, directed or undirected. If you think about the road network, you usually have one lane, two lanes, multiple edges. So to actually model such a network, you need multigraph or mixed graph, or both actually. For sure, you can do a lot of work by just dealing with the sample graph, but that requires a lot of work. So what we did is that we tried to actually build multigraph and mixed graph behind the scene for you. And that whole work, which took months and complex enough, as I will try to show, we'll just resume in a set of 3 functions. So the first thing is that how will you construct a multigraph? If I manage to find my cursor, it's here. Thank you. So we just use the same constructor we have. Graph is a constructor and a representation of the object. So if you just, specify the same edge twice, you get a mixed graph. And it just works automatically. The auto visualization is there. It displays like any other graph. You can take it and you can do all the computation from it. Oops. And you get the result. And hopefully it has 4 edges. So it works as the one you have since version 8, but it just have more capability, essentially, the constructor, talking about graph. And the other function we also provided is a Q function, just to check that your graph is a multigraph or a mixed graph, essentially. So for mixed graph, as you can guess, if you take the same constructor, you give it a directed edge, and on directed edge, you get a mixed graph. So this is the undirected edge, this is directed one. And as earlier, you can just manipulate it as anything else. So in background, we do the work for you. We have a more optimized representation for those graphs. Every function essentially is duplicate in terms of algorithm and what is behind. We implemented new functionality for each function. So for the set of, so this is just a plot of the set of all the functions we have, which is roughly about more than 200. For each of them, we had to work and implement behind the scene the functionality for you. So we haven't added 200 more functions for you, which work for multigraph or mixed graph. But we did that just by enhancing the existing functionality. And the other thing I like to show, actually, let's see, find a spanning tree. Right. So if you take, for example, in the documentation, and you probably will notice it. Oh, what? Let me enhance, make it slightly bigger. So when you look at the documentation in Mathematica, and you just, oh, this is new. Not interesting. Let's see, find shortest part. So for example, for the old function, if you click on updated, you see down here what we just added. All that enhancement work and making the whole system smart in the documentation is just resumed with one line. So essentially, we say that function works for undirected graph, directed graph, weighted graph, mixed graph, and multigraph. And you can imagine each type of graph, have probably his own algorithm and his own automation behind the scene. So, and in short, this is the way we introduce that whole framework. And currently, Mathematica is actually the only system, as far as I know, which actually can support all these types of graphs. So, okay. Now, how do So let's see. So that's essentially what we talk about, multigraph and mixed graph. There will be a talk Friday about advanced, workshop on, advanced graph theory and such a thing. So if you want to actually understand the details, how we implement it, and how to use your functionality to make it more efficient, you can attend that talk. So now I just present in short what we provided. And just to show also, the power of the functionality as well as the design we put in place, most of you know the Euler problem about this, no, not the Euler problem, but the seventh bridge of Königsberg, which was solved by Euler, which essentially asks you to figure out if you can, cross all the bridge in a certain way. So currently in Mathematica, you can actually model this object. This is a graph. And you can use Eulerian graph Q to actually know if the answer is correct or not. So in 2 lines, you model the object, and you do that. And modeling this object is actually quite simple. It's a graph, and all I did is to put the image on the background. You go to Wikipedia, grab the image, do an epilogue of the graph, and then you get it. And if you teach to kids, this is actually quite educative and quite clear. You just see there. You have the bridge, you have the graph. OK, so this is essentially what we did for mixed graph. A lot of functionality behind, quite powerful. So the next one was essentially also 3D visualizations. So what we did essentially, we made graph able to plot in 3D. So that functionality is just purely for drawing. It doesn't affect anything in terms of computation, up to one function, which I will talk probably later on. So let's see how we do that. So essentially, if you have a random, I will just generate a graph. Random graph. Perfect. So that's a random graph. It's rendered in 2D. So what we did, we introduced a function we call graph 3D. If you take that graph, you map it back, you get a 3D representation. You can manipulate it, rotate it, compute on it, or you can even project it back in 2D by just doing graph on it, and it maps back. So there's a high fidelity on both sides, and it works smoothly for you. And all these are just graph objects. You use them as you want.
What's the head of the result of the graph?
It's a graph. So the fundamental object there is a graph. The only difference is that this is a constructor. Only a constructor, we just set up an option, plot it in 3D. So it's just the visualization side, which actually just changed. So nothing different. And actually, let's see if it's actually the case. Head. It's a graph. So as you can imagine, to be able to do that, we have to actually write new algorithm for each of the layout we have. So I think we have about a dozen of layout. From Spring Electrical to basic circular embedding, we have to write 3D version of those layouts. And we actually did that, and we support all of them automatically. So as soon as you do graph 3D, if at the beginning you have a Spring Electrical embedding, we run the algorithm, but in 3D, and then we provide you the appropriate layout. So that works automatically for you. You don't have to do anything or implement anything else. And actually, in that whole fund, we actually went further. Why don't we do ND? It's always good to generalize. So actually, behind the scene, you can actually do the embedding in ND. But unfortunately, we can just draw it in 3D. So the day we actually be able to show higher dimension, we can do that. So this is a basic example where you take the hypercube, and then this kind of show you after picking two different projections how it looks. And the function, if you want to get the actual coordinate of your embedding, you use graph embedding, Spring Electrical, and this is the dimension. You can go to 20, the whole same algorithm will kind of scale and automatically do that for you. So again, behind the scene, we do all the functionality, all the work for you, and everything just works smoothly. Okay, so that was mixed graph, multiple graph, and this was 3D visualization. So these were the main big functionality we added under the hood for you. So as usual, we decided to actually enhance more functionality based on suggestions from different people. So one thing we did is that we introduced new constructors. And one of the most commonly asked was spamming tree. So we have an implementation of spamming tree, extremely fast, one of the best out there. And it works also for all the type of graph, from weighted graph to multi-graph and such a thing. So we support it globally on the set of functionality we have. But also what we did is we provided functionality for graph editing. So if you want to manipulate or edit your graph, so vertex contraction, which can contract a set of vertices, and edge contractor, which contract a set of edges. And link rank here is just, you just have to drop it somewhere, but it fits in the set of functionality of page rank, which was associated to social network analysis. So the group of functionality also we added was about pattern cycle. So we have been seeing a lot of requests from users about being able to find paths beside the shortest path. How can I find 20 paths from point A to point B in my graph? So we introduced find path, which return you a path between two vertices. You can decide to find 20 of them, 1,000 of them, or all of them. We found them, and we return them quite nicely. And it's really fast. But also what we did is that we provided also some specific functionality about finding paths. So if, for example, we provided find independent paths, where essentially you can find paths which doesn't intersect or doesn't share a common vertex, a common edge, essentially. And what we did also, we introduced a set of functionality about connectivity, which also related to paths. So if you can connect the two vertex using two different paths, it's two connected and such a thing. So it's essentially what we did by providing all the K-connectivity functionality. So you can go to the documentation. All those are well documented. There is nice example, good illustration for you to actually see and try to understand the functionality and when you need it and when you can find useful for it to apply it to your work. So the other set of functionality we decided to introduce was about cycle, not too far from path. So we introduced find cycle, which is similar to find path. So essentially it gives you all possible cycle too, or a finite number of them. But if you do math or you love math, in principle, you know that all the cycles create a vector space over a finite field of all the theory around. So we kind of decided to introduce the appropriate functionality to actually analyze it. So if it's a vector space, that means there is a basis. So we introduce find fundamental cycle and edge cycle matrix, which are essentially representation of basis. Each basis have a specific property. So essentially it's that. And also what we did is that we enhanced find shortest tour, and I will probably discuss a little bit later on the enhancement we did for find shortest tour. But what's special in this version is that it works on graph, it works on geoposition, and it works on strings as before, but it's more fast and more efficient. And I will show some examples. Okay. So the next set of functionality we also introduce or we enhance essentially is about find isomorphism. So before our function find isomorphism can just find one isomorphism. So currently now we can find all of the isomorphism you want between two graphs. And also we introduce graph automorphism. So this is kind of hardcore graph theory if you are more interested on that. So essentially which give you the group of all automorphism between two graphs. And you can actually do a lot of, yes? Yes. Yes. Right. Oh, sorry, probably, yeah, mistake. Isomorphism between two graphs or two different graphs. But yes, automorphism is on the same graph. Yes, thank you. And by the way, if you're interested to actually see the application and the use of this, you should probably go into the talk of Theo. I don't know at what time. I think it's tomorrow on tiling. You will see actually how he used it to do quilting. And it's quite interesting and it's quite beautiful. From the use of shortest tour to cycle and such, we see all the application he used how to actually do quilting on his huge milling machine and such a thing. So. Okay, the other functionality we also introduced is canonical graph. So essentially, canonical graph use a canonical representation of graph. So if two graphs are isomorphism, the resulting graph is the same. So we also return you the canonical graph of a graph. So that's actually and more, if you actually have 10,000 graphs and you want to check that they are isomorphic, instead of calling find isomorphic on each of them, you can actually just map canonical graph on them and compare if the results are the same. Two graphs which have the same canonical graph are isomorphic. So if you just take any graph, right, let's take the Peterson graph. You apply canonical graph there, you get another graph. The thing is that that graph is unique in the term that if any graph is isomorphic to the Peterson graph, then his canonical graph will be the same as the Peterson graph. So let me show you a basic example. So this is the Papius graph. This is canonical graph. So if you build any graph which is isomorphic to the Papius graph, you will always get this same graph. So it's a kind of a unique object which represents your graph in some way. And one advantage, especially if you do bioinformatics and such, when you have 10,000 molecules and you want to actually analyze them, usually what you do is you compute canonical graph. Right. Thank you. And also it's kind of useful also in terms of, for example, we have graph data, which is essentially a database of graphs. So essentially, if you can actually compute the canonical graph of all of them, so every time anyone gave you a graph, you just have to compute this canonical graph and map it to the database, and then you can return the property of the graph. So that's one way you can actually extend that functionality, which also kind of more requested by Eric because we want to build it in Wolfram Alpha, where you can give a random graph and we map it to our database. So the next set of functionality we built actually was about relation between graphs. So we introduced transitive closure, which is more the reachability graph. So if you take a graph, you try to find all the vertex you can reach from one vertex to another one. So it's more reachability. And it's quite useful. And also we introduced the converse operation, which is transitive reductions. So what's the smallest graph? Such that if you can reach a point to another one, will actually correspond to the transitive closure of that graph. And the last set of functionality we introduced was about polynomials, which I don't see here. So we introduced total polynomial, chromatic polynomial. These are invariant polynomial for graphs. So if two graphs are isomorphic, have the same type of polynomials. So this is slightly more hardcore number theory. These are the corner where some people were saying we haven't covered, and we decided to go there and cover them. So to be just sure that we cover all the ground for people to do graph theory in the system. So one way to actually show you the power of this whole system, for example, you can generate a maze in 3 lines using spanning tree, and you can actually solve it and visualize the result. Right, one bracket missing. There. Which is just a game of changing the style and generating the maze. So you can actually build maze and solve them in Mathematica quite easily. The other application, which actually came because we were working on releasing the system, and we had to build some nice page so that we show the functionality. We end up looking for some nice application, and one of the, I was looking at NPR series on Power Hungry. I don't know how I end up there. And then I saw this network they had, so this picture. And then I just wondered, can I reproduce it in Mathematica and actually try to analyze if the power grid in the US is robust enough? Is it possible? So quite easily, I took the picture, I copy and paste it, do it in image adjust. And essentially, I wanted to do a morphological graph on it. But also, I wanted to map it on the actual map so that you actually see it. So I call our geographic function, got the map of the US, the continent, America. And then I did a morphological graph. And then I got my network. So this is a graph with a network, quite similar to that one, exactly similar, actually. So you can actually model in 2 lines or 3 lines that original network. And now you can actually start to do analysis. You can figure out, what are the subgraphs, which one can sustain failure or attack or anything like that. So if you're in that field of trying to enhance the power grid in the US, in 3 lines, you can actually do that and really analyze the network. I will just slightly short in terms of, we enhance also the performance. One of the performance enhancement was essentially about the shortest store. We added Concur library which is one of the fastest solver for TSP. You have it in Mathematica, and you can actually solve the shortest store and do some nice animation like this one. Essentially, we took all the city in the world, and then just find shortest store on it, and then generate the map with a nice animate and such. And moreover, you can actually do more interesting things. Essentially, you can do TSP art. So this is an image of I believe you all recognize Steven. You can actually take the position. And since 5 shortest story is so fast, you can actually solve it in a couple of seconds and do a continuous line drawing of the image. So let me just resize it, and then you actually see that it's the same piece. And you can even do the same for Mona Lisa, which have millions of points. So you take a couple of seconds, and then you will see at the end a nice Mona Lisa. People spend their lifetime playing with that and calling it TSP art and generating nice things. But you can do that now in 1 or 2 lines in Mathematica. Right, so Mona Lisa is taking some time. So in short, we provided support for multigraph, 3D visualization, capability, enhancement. Oh, she came back. Fantastic. So this is a continuous line of Mona Lisa. So anyway, to conclude, you can go to our marketing page. There is good documentation there. You can see the list of feature page. And if you have any question, you can ask Roger, our R&D director, J-Bomb, and Jan in the room, so about graph and network. So thank you.